Okay, perfect. Thank you. Okay, finally we can get started. So I welcome you very much to our lecture on electricity and magnetism. My name is, as I said earlier, I'm Johannes Russer. I'm with the Technical University Munich. You see here my email address, that is jrusser@tum.de. You uh, um, may this is the best way basically to contact me if you have any questions. And I'll give you now a bit of an introduction what this lecture is going to be about, and what is the scope actually of the lecture here. So the lecture, as the title implies, about electricity and magnetism. So the aspects are is more or less how electric fields are made. They are caused by electric charge, or at least when you are looking at electrostatics, then the cause for the electric field is the electric charge. So we will look into what actually the electric field is. It's kind of a very, in some way, intangible thing, because it is something that you cannot really uh, it's invisible, and it becomes only it basically only materializes its effect in the presence of a further charge, because then you will see that it is responsible for exerting a force on another electric charge. So from the electrostatic aspect, then we move to charges in motion. So that means when you have an electric current, and that electric current, it will be also uh, triggered by some, yeah, maybe by some electric field, but it also is a source for a magnetic field. And so you have these two aspects, electric and magnetic field, and eventually uh, when you combine these two, you have to add a bit more to it. You get to uh, the electromagnetism. This is Maxwell's equation. These are really actually the fundamental equations. So if you have the full set of Maxwell's equations, you have also all the things what you need then for the electrostatic or the stationary magnetic fields. And this is then basis for the electromagnetic phenomena. So this is really some very fundamental laws that we have in physics, and is the underlying basis for um, a lot of the technical, um, well, uh, on the devices and what we have today, what basically defines our modern life, the electronics, or not defined, but which is a very critical, very firm, an aspect that touches in our life at every aspect. So it is important, if you want to understand how electronic devices work, how electric circuits are working. It is obviously the foundation for the understanding of electromagnetic waves, which we need for communication also. And in the end, which is also the phenomena which is also explaining the light, because electric wave, just depending on what frequency you can use them as radio waves, or they are also the visible light and beyond. So let me talk about some organizational things here. So you have seen probably that the lecture notes are already available on X site. These are more elaborate than what or they will also contain even more detail than what I will present you in the lecture here itself. So you can use those for further reading. We also given there derivations of all formulas, which are given in the lecture, and there may be more detail also in there than what I can present you in the lecture. Then I will also present you with some gap text, so to say. So there are some texts where there is a little bit of so there are some sheets where there's some text already included. I will use that to present in the lecture in further detail. I will give you some right here on the screen to fill in the details so that you see how the matter evolves. And these gap texts, they will be also put up on Excite. Right now, they are not yet on there, but then you can use them to also write along in the lecture, or I will also present you the taken notes then on Excite, but you can take your own notes there on those. Then there will be also some tutorial that will become available on the website. And this contains the problems that we will also be working through here during the electricity and magnetism tutorials, basically the part aside on the lecture. And we will do at least, we will do some of these problems there. There are probably more problems than we will work out in class, but you can also use those other problems, or also these that we are having in class. You can use them, of course, for practicing. Also, there will be some other examples and applications which will be shown then during the lecture, and there should be also some sample exam problems to be practiced then. And then there will be some problems, some sample exam problems and solutions. They shall also be made available then towards the end of the lecture time online. So about the schedule first, for giving you further reading, you know that this is our first online session today. The next will be on January 12th. And that will be Monday week after. And the third one will be on January 20th. That will be a Tuesday, again the week after. And then in the week subsequent to that, I think the 26th it should be, that I will be giving you the lecture in presence in the institute, and that will be till February 10th. And we will have then a block of lectures in the morning. I believe it's most of the days it will be by 9:30 to 12:30. And then also in the afternoon, there will be also some further lectures. So this will be then in the morning, in general, in the lecture, in the afternoon, the tutorial. But since I will be giving you both lecture and tutorial, we are also a bit flexible so that we can adjust it as it fits well into the in our progress as we advance, so that we can pick what is fitting well. Also, these slides that I'm showing to you right now, I also will upload them afterwards on Excite. You see there's a bit of literature that you can use if you like for further reading. you want to, it's often useful to see things from different perspectives or from have multiple works that you can um, consult to um, yeah, deepen your understanding. And the books that I like to recommend here is, for example, the book by Purcell, Electricity and Magnetism. Then there's a book by Branislav Notaros. It is called Electromagnetics, Magnetics, Prentice Hall. And the book by Griffith, Introduction to Electrodynamics. Then the book by Jackson, which is also quite a classic book. It's called also Classical Electricity and Magnetism. Furthermore, um, what is useful is to have books that give you the mathematical formulas, so, formula that you need. But there will be also some material that's provided, of course, in the lecture, but it is good to have these um, mathematical books like Bronstein, Handbook of Mathematics, or the Rade Westergren, Mathematics Handbook for Science and Engineering. And also, if you're interested, there's a book on vector analysis by Brown and Kendall. And yeah, so these slides will be also up, and you can also look at these um, references and follow those books if you like. So information on exam, the date is, to my knowledge, I think February 20, but I put in there a question mark because I'm not 100% sure whether this is I'm still up to date with this information. So you probably have also some information maybe available. Maybe you can tell me if that is matching to what you are aware of. Otherwise, please let me know. And of course, we still have some time. We can update this information. Duration shall be 90 minutes. There will be a closed book exam. There will be, oh, you have no current info. Okay, thank you. So um, this is information I have noted down, but I'm not sure whether it is really the last information. So quizzes, the questions will be the quizzes um, during the lecture. Oh yeah, actually this is a good point. So right now there's an exam plan. We maybe can do also some quizzes. So that uh, is a nice comment there. I will get back to that. Yeah. And yeah. So we have the exam. The quizzes I will take a look into also. And then for the exam, we will also distribute some pages with mathematical formulas and also basic formulas from the lecture. And then we will have questions, short questions, and also calculation problems to solve in the lecture. So also, what is yeah, also mathematical formulas, they will be uploaded. So you will get some sheet with some of the important formulas. So then please concerning the content of the lecture, we review the lecture so in timely fashion after the lecture that you can follow the lectures and tutorial on the subsequent ones so that you're always up to date. Also regarding the problems, please try also to solve problems on your own. So without taking a look at the solution, and then we will also work on the solution here in the tutorials, and that will give you the um, skill really to work on the problems also on your own. It's then it's also needed in the exam, also in general. And that's the point that you can then be comfortable using the techniques that we are um, describing here. And that also is a good preparation in the end then for um, the exam. Also, please try to get first a deeper understanding of the physical principles, and then to get a routine in problem solving. And yeah, this is required for the exam, and we also will provide some sample problems for exams. And if you have any questions, please also send them to me by email. This is my email. I have to answer them in a timely fashion. And also, please, you are welcome to ask anytime during the lecture. Okay, this has been more to the formal aspects. You have questions regarding those. Okay, then let me introduce you a bit more to the contents, give you an overview what we will be covering. These are four aspects: the electrostatics, then we have the stationary currents, magnetostatics, and induction. So the electrostatics is about how electric fields are generated and how can be calculated, what is relevant in this respect. We want to talk about charge, electric charge, the electric force, electric fields, and in all that, we all remain at the static aspect that obviously called electrostatics. This is probably these four sections that we have are different in their extent, how much we have to cover with them. That is probably also the larger part here on the electrostatics. Then in the next chapter, we move on to currents. So that is the aspect when the charge starts to move, because it is within an electric field. But what the aspect here is that it is stationary current that we are looking at. So there is no time variation in the current. So the current, of course, is something where you have a number of charges which are changing their position with time, but this change, they keep going with a, so to say, constant velocity, and there's no, the current remains constant, so that is not time variant. So in that sense, it is a stationary current. And there we look at the electric current. We are looking at the concept of the current density, the transport of charge. So you can compare that also then how one is looking at that when you look at the circuit theory. And also we will look there at Kirchhoff's current law, and we will make connections to the circuit. So in the end, when you get more familiar with this topic, you will see that we are going towards Maxwell's equations. As I mentioned earlier in this lecture, we will find goal here in this lecture is to have introduced you to the Maxwell equations, Maxwell part of Maxwell theory then, and from there you can go back then to find all the aspects of stationary magnetic fields or electrostatics, and it also allows you to look at these basic principles of circuit theory, where, for example, Kirchhoff's current law, also the voltage law. From these stationary currents, we go into magnetostatics. So if the current is stationary, the electric current is responsible for the generation and causes a magnetic field. So we will look how this relation is between the electric current and the magnetic field. How can these magnetic fields be calculated, and what is happening in a static magnetic field? And then this is already one kind of interaction, you could say, between the electricity and the magnetism, that the electric current is causing a magnetic field. But then we also go into the induction, and that what is this about? This is what happens if something is varying with time inside a magnetic field, and this will eventually bring us to Maxwell's equation. So now you might wonder, why are we doing this? Why is electricity magnetism, and in the end then also the electromagnetic equations useful? Why? Well, for electrical engineers, as you know, this actually probably quite at the core of what quite at the core of electrical engineering. So you see that there are quite a few electrostatic phenomena that are surrounding us. So you know what happens from the concept of electrostatic discharge. This is a critical aspect also when you are dealing with electronic devices. You know, they are sensitive to that. We see electrostatic discharge in thunderstorms, or let's say the electrostatic phenomena is causing that what then results in the lightning. At that point, it's of course not a static phenomenon anymore when the discharge is happening. Then static is important to when we're dealing with electrons, when we are dealing with atoms in solid state materials. So in all these aspects, we have to know our fundamentals on electrostatics and also on magnetism then. And as for the technical applications, there are probably a myriad of examples. One can think you have, of course, very important the electric or electromotors and electric drives. So if you think of an electric vehicle, or if you think of a train engine, you have these electric motors there. But also if you have your electric toothbrush, then there will be also a tiny electromotor inbuilt. And of course, if you go to a power plant, then you have large generators, which is also in the end the generator and motor are quite tightly related concepts. And you also have electric drives. You know that when you are looking into any maybe processes in some industrial applications, that you need some uh, controls, maybe of valves, or um, these will be then controlled by some electric drive. So you will also have some kind of small motor or some other actuator that is based on these electric and magnetic concepts. So needed for electric energy conversion and generation, but also on the small scale, needed in the device physics. We look at semiconductors. If you, um, if you understand semiconductors, then you have to know the behavior of electrons in some lattice, and so also even of course semiconductor devices will go far beyond what we are doing here in this lecture, but in this year will be something also that is relevant to understand those as a foundation. And yeah, you have sensors that all are based on this effect. So this phenomenon. Here you see a picture of a lightning striking down over a city that is an discharge of that has happened after a charge has accumulated in the atmosphere, and the potential difference to the ground has become so significant that it yeah that this discharge is about to happen. So this is a very loud phenomenon. But you see on the very smaller scale, you see here this little finger, and there's a little spark flying on this device. You have this same or similar, pretty much the same phenomena on a very small scale. You encounter that as well. And this becomes then also very critical if you look here on the right-hand side. You have an electronic circuit board. You see the different transmission lines here that connect different parts of the board, and on this board you will eventually also put electronic components or integrated circuits. And if you are touching such a device and you happen to be charged electrostatically, you get too close to it, then some discharge can happen suddenly. You will also possibly see a small spark like it is depicted here, and you can actually destroy your electronic circuit quite easily, because these even these voltages that you can accumulate. This is kind of so some. I will show you some picture as some more details how this can happen. But this discharge, the voltage can be in the hundreds or thousands of volts, and that can be easily sufficient to destroy some sensitive semiconductor devices. Even though the current is very minimal, because the charge that is being discharged in the end quite little. So this here will relate to chapter 1. This is the electric fields. This is electrostatic discharge, and it also relates to chapter 2, which is electric current densities, where we talk about joule heating, and so you see the scale variation is quite large. What you also, where you also need this knowledge of electricity, magnetism, or electromagnetism, as you combine those aspects, is of course for the design of integrated circuits. So there you have a strong need for knowledge on electromagnetics. So what are the issues? You have electromagnetic crosstalk. It concerns the design of the wiring, also how much current can flow, what's the robustness with respect to temperature. So what is electromagnetic crosstalk? You see you have here this printed circuit board, and it connects different devices. These devices might be also like of some integrated circuits and chips that you place, where you place multiple on the circuit board, and these chips have to exchange information. So you put in signal lines between those, and you see that you see some lines here. These are basically guiding the electromagnetic wave, and in this electromagnetic wave, it is basically the carrier of some signal. By giving the right modulation, it carries information. And when you have here a multitude of signal lines, and that is what you will typically have, because you have a lot of outputs, maybe possibly at such a chip, and you want to send these to the input of another chip. So you might have a set of parallel lines. In each of them is carrying the electromagnetic wave that has a particular signal modulated onto it. And these electromagnetic fields along these lines, however, are usually not confined solely to the line. So you have different ways of how you can design such a line. Commonly, you might have something like what is called a microstrip line, but the field is not solely confined to that line, but it actually is guided by that line, and the field extends to the outside of this metallization layer. And so what happens if you have multiple lines close to each other, then the field of a neighboring line is affecting the field of the adjacent line, and you have interference, and you can have crosstalk. You can, of course, design lines so that they are perfectly shielded, but this is often not what you want to do, because this can also reduce in the end the performance of your device, because it will need more. Also, you likely have to enlarge the whole structure, and these are aspects that you don't really help. It's not helpful if you want to get a very high performance. So in the end, you want to design something maybe that where you also make kind of a compromise in terms of you allow for a certain level of crosstalk, as long as it is not so bad that it is hampering really the proper function of the device, but you can maybe able to get higher overall performance out. And so you have to balance out the pros and cons if you design such a device. And so you have to be aware of what effects you have, which one are deterrent or deteriorating your working of the device, and to what degree, and what you are willing to accept from an engineering point of view. Yeah, so design of wiring, also when you go into electromagnetics, then you will see you have these lines that carry signals. You want to have devices which are, for example, if it's some digital or also analog circuit that is processing something, you want to have that usually at high rates to happen. That implies usually also that you go into high frequencies, which offer you high the option for high processing speeds and high bandwidth. And then you get into the area of high frequency engineering, where actually the length of the line becomes critical, and becomes critical to the operation. And so, of course, you also, as pointed out, you're interested about losses. You have here usually copper lines have some degree of losses, and you have heat generation, and these are all a lot of plenty of physical effects that you can and actually have to take into consideration when you design some complex circuitry. So this is the outlook. We cannot go into the effects of crosstalk here, but our goal is electromagnetic equation, so Maxwell's equation, how the interaction of the electric and the magnetic field happens, and how it is actually one can cause the other, and sustain electromagnetic wave that is traveling. So related to what I've mentioned, however, are now in chapter 2 with stationary currents, and chapter 4 with electric induction. So what you see here is a small microphone. It's a capacitive silicon microphone. You find it present in nearly every mobile device. You see, this is device here. But if you want to have a schematic, then how it is really constructed, you see that there's a small membrane here. And you have here this housing, this capsule that goes around the whole microphone. You have an opening here. And as there is some sound, the sound is carried by variation of pressure in the air. And it will cause here the membrane to bend here towards backplate. And the backplate and the membrane together here, they form a capacitor. So we will also look at what capacitor is. The capacitor is able to, on the one hand, it stores charge, and this ability to store or to retain charge of a device, well, basically the capacity, that is a measure of how much charge at a given voltage applied to conductors, how much charge can be accumulated on these conductors. That in this example, that here defines here is an underlying basis of the operation, because as you have the wave incident, this main membrane is getting bent, and you change the distance to the backplane, and that affects the capacitance, and you can monitor the change of the capacitance, and by that way translate this change of pressure variation in the air to change of capacity in an electric circuit. And so you have a sensor that captures the sound. And this also is an part of, or also chapter 1, where you deal with electrostatic charges, electric fields, and electric capacitance. This will help to, um, it will be useful to deal with this type of sensor, how to describe such a sensor. There's another example you have here in indigitated capacitor. You see also, oops, you have here, here is your 3D view, and you have the two-dimensional view below. You see here these two orange structures. These are some conductors, and you see digitated, that means the digit is basically the originates from the word for the finger. It is, and you see here very much these like a set of fingers on each of these structures, and they are kind of gripping into each other. The advantage here is now that you have here two conducting surfaces where you bring a lot of you have here the outline of your surface here, and you bring that close to the outline of the second conducting structure, and you do that over you maximize, or you do that as a large of possible um, um, outline where the two structures get very close to each other. And in the end, what we will see in the first chapter is that our capacity is depending on the one hand on depends on basically you have two conducting structures. The larger these structures are, the higher you can get your capacitance, and you basically maximize here by this interdigitated design here your surface where they interact, and you also have to get them as close as possible to maximize the capacitance. And so such an indigitated capacitor can bring here on a small physical fingerprint quite a large capacitance effect. And what you do then subsequently here that you see on the right-hand side, you have these two indigitated structures which form this capacitor, and then you bring on the top some, for example, some polymeric layer, and that layer, in the specific case where we have here a gas sensor, has a property that once exposed to a certain gas, it changes its dielectric properties. And for that reason, the capacitance, which is also defined by what is in between these two conducting structures, the dielectric medium, if the dielectric properties are changing here, then your capacitance does so as well. And you can use such a device as a gas sensor. Relevant to this is again chapter 1, electrostatics, electric fields in different media, and electric capacitances. So what are your, so to say, friends for this lecture, for the electricity and magnetism? Is you should be well familiar with vectors and vector fields. We'll also give some little some recap or brush up on some mathematical aspects. So you should be familiar with vectors and vector fields. Also, very important is the concept of gradient, of divergence and curl. You should be familiar with doing integrations, and that for the three-dimensional space. So that includes integrations along curves, areas, and over volume integral. And then we also have to look in the different coordinate systems. For us, there would be the Cartesian and the Newton, this very good coordinate system of relevance. If you know the way you integrate new integration, you have to I don't want to say it's different, but you have to look at the certain um, properties of these coordinate systems so that you do your integration properly. So we're going to take a look at that. So we will recall and practice the basics in the context of electricity and magnetism. And also, second aspect, this first aspect here was concerning the mathematics. Now, what is important for you for this lecture with respect to the physical aspect? Electricity and magnetism is kind of a, so to say, electrophysics. So you should remember the following things, what you have learned in the physics lectures. And these would be what you've learned about force, momentum, and torque, what you have learned about the conservative forces, what you have learned about potentials, then what you've learned about energy, work, potential, power, and also about the conservation laws. Also, we will recall and practice the basics here within the context of this the topic of this lecture. Yeah. Any questions to this file? It's very happy if you interrupt me anytime. So, but I know, especially in online lectures, it's often a bit okay. Thank you. It was easier to bring in questions usually in the in presence lecture. So let's look at the international unit system. So there has been some change a few years ago, and that was in 2019, concerning the definition of the standard kilogram that has become now unit that is also based on natural constants. So this happened in 2018 that it had been decided that there should be done a fundamental change in the international standard unit system, also short as I. Before, you already had the second and the meter had been redefined by natural constants. So you know the second has been defined based on an atomic transition frequency on a specific one, and the meter then you can, once you have the time fixed by this atomic transition frequency, you have also another natural constant, which is the velocity of light in free space, and that we can use along with the time to define the meter. The original meter was defined by no, sorry, what I wanted to say, the original kilogram, because we're talking about what the original meter was just defined as a, yeah, there was a physical unit that was decided to be the meter. And with the kilogram, you originally had that the kilogram is defined as the weight of 1 liter of water. So you basically use the meter as an underlying unit, and then you know that 10 centimeter cube gives you the volume of 1 liter, and then you fill into this defined space water at the proper temperature, which originally was 0, and then they went to 4 degree, where it has its highest density. So you put 4 degree cold water into um, space that counts for 1 liter, and that gives you 1 kilogram. So now this definition has changed, but in total we have here we have 7 defined constants in the SI system, where we have some where we have some exact values which are then fixed, and along with that we have 7 base units which are expressed by these natural constants. Here we have these these 7 SI units, and we see that also again here on this slide here. So we have the time that is defined by the transition frequency, and we have the length that is then defined with the speed of light in each space, along with the transition frequency of the specific atom. And now for the mass, we also take the Planck quantum of action, which is in 2 times second, or in kilogram meter square per second. So if you are combining that with the previously set units for meter and second, so you need also the speed of light and the transition frequency, then you obtain the definition for the kilogram. We have then further electric current, which is given in ampere, and for that we need the elementary charge to define it of an electron. That is given in ampere seconds, the charge. So along with the definition of the time, you can get to ampere. Then we have here temperature, molar amount, and light intensity also. These are the 7 SI units. Then what you should be also familiar with, of course, is the unit prefixes. Here you know those, but I've summarized them up here anyway. This is to which power you are at. If you, for example, 10 to the minus 18, then you have some atto approximately A, then 10 to the minus 15 goes down, then it's femto, and you're getting increasingly larger powers. 10 to minus 12 becomes pico, 10 to minus 9 nano, and you go into micro, milli, centi, and deci. And then if you go up to higher power, you to the from 10 to the minus 18 to 10 to the minus 1, you go up to the larger ones, 10 to the 1 to 10 to 18. There is deca, hecto, kilo, mega, giga, then 10 to the 12, you have the tera, 10 to the 15, theta, and 10 to the 18, exa. So, and also a useful chart is because we use a lot of Greek alphabet in order to extend also to denote variables and constants in order to have more available. Just for example, in Latin alphabet, you have here a chart that can be also handy to look at. So whether you need to memorize it, um, no, well, let's say it usually is helpful to know some of them which are reoccurring, because we will not use all of those here, but you know that alpha, beta, gamma is very often used also, the small ones, in particular, mostly the small ones maybe are more important. Alpha, beta, gamma, or the epsilon is used for the permittivity that you should memorize. Delta is often used for some difference. The mu is used for the permeability. Lambda is often used for some length. So I think those you will notice which are frequently the sigma we use for. So I think, yeah, I think some of them you should probably memorize. So these would be certainly, I think those here. Um, these some of eta, etc. also come more frequently. The theta you have often for the angle. And you will notice that they repeat. And so, yes, I think, of course, phi and um, omega for the frequency. Yeah, in the end, if you are memorizing the shape and you have forgotten the how what it is called, it's not a strategy or vice versa. I mean, in the end, you have to know things consistently, but it is not. Um, and it is helpful as you keep running into those. Sigma is also um, for the when you look at the resistance of or the conductivity rather. And rho is also often used in terms for alternative to the R for the radius, for example. So I think, yeah, you, as you keep using them, you will memorize the relevant ones. But you don't have to memorize everything. I mean, especially you see that the capitalized ones are not so often used. Okay. Then, well, that, but I'll put that up next slide and you can use it as a reference. Okay, then I'm through this first introduction here and I'll pull up the next set. Just give me a second. So I'll check also, because we have also our participant list here. I think I should believe it is recorded anyway, because in that sense we don't need to. I'm just thinking of the attendance sign up, so to say. I think that is automatically captured here with Zoom. Just give me a second, please. And then now it's just because I'm asked to also the attendance sheet, and I want to make sure that I'm also provide that actually. I can't see it right now, but I think it should be possible. Okay, let's get into the first part of chapter 1. Here, an overview. Here we are looking at the electric charge now. That is our first aspect, and I want to give you some historical backdrop about electric charge when it has been discovered. So it is considered that it goes back to the old Greek, who discovered it around 550 before Christ. So that is about that was by Thales of Milet or Miletus, that is at, in, well, actually it's nowadays Turkey, with the Mediterranean. And how was it discovered? So I think um, might have been discovered also earlier, but there is basically recorded evidence of that. And the name electron is actually Greek for amber. And what happens if you take that incidence, I think it was reported to be some cat fur that is being rubbed against an amber. You see here a piece of amber, basically that is fossilized um, tree resin, and you can find it in rare occasions on the shore of the ocean. Um, and it looks very lovely, amber colored. So if you rub that, then it turned out that this is quite a good material uh, to cause some uh, charge separation, so to say, um, when you rub it. And that was observed then. So the amber attracts then small and light things like leaves and feathers if you rub it with this tissue or with this fur. And the effect that is underlying here is actually called the triboelectric effect. That means that by rubbing two surfaces of different um, based on different material, that you can have a charge separation. And as a consequence, you have then one of these materials charged electrically, either positive or negative, positive and negative. I'll get to that also in a moment. And so as amber is called, or the amber is called in Greek electron, the name for the charge also has been coined then electron, that is basically just amber. What is special about charges? They are not visible, but they have an impact and also an effect which is observable. What you see here on this side, there's a girl that holds here this rod, and she has charged this rod also by rubbing it on some tissue, and then has made this small snake here. This is basically you take a very lightweight piece of paper or some paper tissue, and then it's cut around like in a snake shape. And then when you touch it with the rod, then the paper starts to stick to it, and you lift it up, and the snake basically follows that. It adheres to the rod, and she's lifting it up along. So they're actually quite nice things that you can do to observe the electric static effect. You see here also um, something out of, well, daily life. It depends actually how frequently one is visiting the playground, but also given it is a special incident, you will not always have such a nice effect. I play you that clip here. You find that also on YouTube. There's a little child sliding down the uh, slide, and you have to look at the hair. It's quite nice. So also here you have this triboelectric effect. The child is sliding over this surface. And now, of course, depends on the specific materials, what the slide is made of, and the type of clothes the child is wearing. And then charge is being separated. And so why is this hair now standing like that? Because the child is getting charged positively or negatively. The property of charge is that the charge carriers actually repel each other if they are of the same type. And that means they try to distribute as far apart as possible. And so they will distribute over the body, over the uh, hair also. And since they are repelling each other, the hair starts to stand up like that. So this is a nice effect. You can observe electrostatic. I have here another example where you have electric charge, and where they do several experiments. So you can actually observe the existence of the electric charge. I mean, indirectly, because we can not see the charge, but we can see the effect that it causes. And these are also some experiments here that very safely can be reproduced at home, also without destroying anything. I'll play you that video of that you can find on YouTube, and I've given the links also at the back of the slides. So the slides will be available as PDF. You can look at the link and look at the videos again if you like. But and this is quite nice because it shows you how you can observe some physical effect with actually quite moderate means. What you see here is they use here some styrofoam plates, and they use a cloth, a towel, and they rub them, and then they make them hover, and they do more tricks, not tricks, but more experiments until that you know it is repelled from the other plate and just pulled back by the hand, but it doesn't want to fall down. It just leave it and it will rise up and eventually fall to the side. Also here we should wrap the rod with the cloth, and now it can be based on different charges that we have on this soda can, and on the rod you can pull the can towards the rod. Here you have some soap bubble, and also here you can attract it by this charge rod. So obviously you need something that is very light and delicate, because the force that you can generate depending on the amount of charge, and so this not very strong usually by the charge that you can generate by such a triboelectric. But if you have such light styrofoam things, then you can do that here. And here we have some fluid, some water running out of the pot with a hole in the bottom, and you can variate it. And this is also quite nice here, because in some way it's also a bit like basic for measurement device. So why do these foil plates here, this conducting aluminum, separate from each other as you go? Let's keep watching. Okay, you saw that these two plates in the jar were separating. And that is again like the same effect while the hair on the little child were standing up and going far apart from each other, because you charge these metal rod that you had in this jar here in the second example, or in the second video here. Yeah. And as you put the charge on here, the charge distributes, and it is charged at the same time, so that it repels each other. So these two plates try to get these little thin foil sheets try to separate from each other because they are repelling each other because they both have the same type of charge on it, and so they're starting to um, fall aside. So then we have the not so safe examples. That is the electrostatics in nature. That is the lightning from the thundercloud. And yes, this is of course well known and it can be quite impressive. You just don't want to be too close to it and hope, um, yeah, just to watch it is nice, but it could be also quite harmful, of course. So in that case, you have also charge separation on a somewhat larger scale than with the triboelectric effect. And then if the weather conditions are right, and the separation of charge has occurred in the first place, and then if the conditions are also that the discharge is also well possible, then it eventually will happen. You will have this unlikely strike. But there are also some quite interesting other effects in nature that, for example, includes electric eels, you know, these fish, which are able to generate electricity. And they use this quasi-static electric field for several purposes. They can use it for navigation by also, it helps them to monitor their surrounding. They can sense the electricity and also send out an electric, generate an electric field and see how it is affected by the surrounding. It also helps them to protect themselves against predators. If they are being caught, they can generate an electric, strong electric field that gives some unpleasant sensation to the attacker and will make the attacker abandon the eel. But also they on their own can use it for hunting. They first of all can also see if there's any prey that might interest them. So by sending out some electric shock, they can see if something maybe is animated and starts to move, which they might have not seen otherwise, so they can trigger their potential prey to reveal itself. And then also when they attack the prey, they can paralyze it by electric shock. Then other effects in nature, you have bees and also bumblebees. They actually can feel electric charges from flowers. So there is really an article in Nature that is also referenced in the back, that it enables them to gather information about the flower that they are based on electric charges. And also similar to the lightning from thunderstorms, what one can also observe is in the event of volcanic eruptions, that they come along with kind of a lightning often, or sometimes. So because also there the volcano throws particles into the air, and in the end that triggers also a redistribution of the charge, and eventually it will come to a discharge, and you also can observe lightning in the presence of volcano eruption at times. This example, by the way, that I showed beforehand with the video with the styrofoam. So this can be very nicely done also at home, but one has to be always considering that it is advantageous to be in dry weather conditions. So if you have a lot of air humidity, then usually that is not helpful in doing such experiments, because the humidity will cause this charge to uh, to prematurely discharge. So you want to keep that charge separated, and if you have a lot of humidity in the air, that usually is not very helpful. Then we have electric charge in matter, and that is a very important aspect. The electrical structure of matter, the charges that you have in atoms. So what does an atom consist of? Well, the atom consists of the nucleus, that you see here, and around it you have a number of electrons which are orbiting here. And the nucleus is actually um, um, made of protons and neutrons. So protons are actually positively charged. And then you have electrons which carry a negative charge. So the basically what is negative and what is positive is just a convention. That is how it historically evolved. That one called electronegative, and what is in the nucleus, in the protons, it's positive. But the maybe more essence is that you have two kind of charges, and you actually in general have usually a charge balance, and then you will also not notice any field of forces as long as you have a charge balance. But when you obtain some charge, positive or negative, you actually always obtain both, because you get some negative or positive charge by separating charges, and as you get positive charge, positive charge, you at the same time always generating a negative charge. So the atom consists of that nucleus, and that is positively charged. You have the electrons orbiting around; these are negatively charged, and in the case when the atoms which is usually the case, you have a neutral atom. That means the number of electrons and the number of protons is they're just balancing each out. You have the same amount of electrons and protons. So these electrons are bound to the nucleus by the so-called Coulomb force. When we will look at this Coulomb force, how we describe that. And if you remove one or more of these electrons, you end up with a positively charged ion. And if you add additional electrons, you end up with a negatively charged ion. By the way, this atomic model, what you see here, is quite nice and quite useful also, but of course it's just a model, and one always has to see to what degree a model is useful and to what it is accurate. I'll show you the relations on the next slide. Actually, I would say that these electrons are actually quite close to the nucleus. You'll see that there's quite a disparity between the size of the electron or the size of the atom itself and what is actually really taken up by the nucleus. And also these orbits is also a nice model to visualize, but we also know that this orbiting model is to take a bit of caution in view of the quantum mechanics. Of course, we know that You cannot pinpoint an electron to that degree where it is really orbiting around this nucleus. And the orbits that we prescribe usually, um, they um, they usually give more likeliness where to find the electron, but we cannot really give these specific trajectories and say so the electron is always along this particular trajectory at with a given timeline, like you see here on the picture. Oops, what happened? I don't want to forward, but instead I'm not going onto it. Oh, yeah, good. So you see, I'm taking um, giving some details about the charge already in the previous slides. I mentioned that, but what are the fundamental properties of charge? So from experimental observation and also from experience, we can deduce the following. So charge is a fundamental property of all elementary particles. It's, in that sense, it is comparable to mass. All um, elementary particles um, are also characterized by the charge here. And the other thing to deduce is that charge is a source of the electromagnetic interaction. And this is one of the four fundamental interactions in physics. So you know you have the four fundamental forces in physics, which are the gravitational force, and this is the electromagnetic force. You have also the strong and the weak force, which, however, appear more to the forces on a inner atomic level, and these make up the four fundamental forces. Who has one of the persons who have worked on the development of electricity theory for electricity is Benjamin Franklin, and he has found that charge is actually like a particle. And the important aspect is for this particle that we have two, so to say, classes of flavors of charges, and these are a positive and negative charge. And the total charge in a closed system is always conserved. That means a closed system, you cannot generate charge out of nothing, but you can only have a pairwise generation or annihilation of positive and negative charge. So, like for example, the atom that we looked at, you remove one electron from the atom, then you end up with a negatively charged, which is given by the electron, and the positively charged ion. You see here in the bottom is also a picture of painting of Benjamin Franklin that has been around 1760 that he lived and made discoveries. Yeah. Then let's get to the next step. In 1785, we have here Coulomb, the French scientist. He described then the force between the charges, and then they're depending on the location and on the distance of these charges. And that we will see them in the next section, section 1, 2. We will look into how it is exactly related, the force term. And important aspect is that like charges repel each other. This is what we have seen in these experiment, like the child that has been charged who is coming down the slide, and because the charge distribute by trying to be as far as possible apart. That was the reason also why the hair was raining on the child. And unlike charges, on the other hand, they attract each other. And the research Coulomb did was also not only on electric charge, but by the way, that mentioned here also it's done studies on friction in viscous fluids, on stiction friction, and yeah, also on the electrostatic forces. And so in honor also the electrostatic force is named after him. It's a Coulomb's force. What you see here also is a device to measure the charge. Basically, you have here the so-called Coulomb's balance. And the idea is that there was a picture of realization of it, or the build of that, as you find in the unit in the Deutsche Museum, which is a large technical museum, the largest in Germany, and has a nice exhibition. And there's rebuild of this Coulomb force. And you see here the working you have here a mirror, and you can bring here with basically very thin or some lightweight balance here, where you have two charges here, and you can monitor the force that is being exerted when you bring a second charge here close to this by this in consequence turning, and then you let it stay here, and it allows you to measure charge. The further aspect is that charge also has a radius of action. That means charges, they are influenced by each other, even if they're far away. But the further the charge is away, the force that one charge is exerting on the other is actually also decaying. But the reach out is also quite far. And this effect can then be described by the force field. That is something that we cover also in the section 1.3. And the fifth aspect here, now you see we have, the fifth aspect here is charge is quantized. That means there's a minimum charge that cannot be divided any further. So also that is maybe for a long time, right now we see that we have a world which on the physical foundations at the very bottom level, we have everything discrete, and things come in minimum units that then are not further divisible. That also applies, for example, to the energy that is not something that can be divided indefinitely, but that has a most minor charge, but a minor unit, minor quantization unit. Well, for the charge, that might be a bit easier because it is also very minor, but it's a bit has been established for a bit longer that there is a minimum charge. And this is the so-called elementary charge. And these have been also determined by experiments by once by Thomson in 1897 and also by Millikan in 1910. They have then measured what the actually elementary charge is. In the elementary charge, you notice here this Q for charge. No, that is a common term we denote the charge by Q. And EL is elementary, or also the elementary charge is E, like the electron, and it's 1.602 times 10 to the minus 19, that should be point. And that is Coulomb, and that is the elementary unit of charge, and that corresponds to ampere times seconds. And yeah, all charges that you have, which are larger than the elementary charge, are actually made up by a multitude of the elementary charges. So all separable charges, charged particles, carry a multiple of this elementary charge. So here you have a little overview. This is the elementary charge, 1.6 times 10 to the 19 Coulomb. That is usually also a value that pops up over and over again. And we denote it with E0, or more general, either small or large Q. The units here, on the other hand, is an is either Coulomb, or Coulomb is equal to ampere times second. Then this charge, any charge, is a multiple of the elementary charge. And set here is now integer number, which can be positive or negative, or also zero. If set is zero, then you have no charge. You have the case where you have charge neutrality. If your set is part of the negative integers, then you have a negative charge, and otherwise, if it is positive integer, so it is part of the natural numbers, or the only set plus, then you have this positive charge. So you find only this. There's a rare exceptions when you're looking at quarks, but that will be not relevant for our lecture. Then you can actually have also something like plus minus 1/3 of an elementary charge, or plus minus 2/3 of an elementary charge. But apart from this exception, what we find otherwise is any charge is a multiple integer, positive or negative, of the elementary charge. Oh, I missed the question whether you need to memorize all of that. I'm not sure at what point that was referring, at which slide I was at that. Yeah. These slides I will put on which slide. Yeah, you will find these slides. I will put them afterwards, so you can review them. And electric charge. Now let's look at the properties. You see, you see earlier I had here. You see there's a dot. There was a comma there that is supposed to be a dot here. So here on this slide it is correct. That's which part? That's oh, 1 second. Thank you. I will correct that. That is, I will, on the other one I corrected. It is with. Sorry, there's some German word that slipped in. That is mit is the German for with. I will. Thank you for pointing that out. I will correct that. So, okay, here you see properties of electrical charges for electron and proton, and I think just see that our time is actually lapsed already. It's 10:30. I think this is probably also not a bad place to stop here. And I will continue here you get next week. And yeah, if you have questions, thank you for your strong participation and putting also questions in these in the chat. And then if you have questions, also please feel free to email me. And we will meet again on next week on Monday the 12th at the same time. And that will be our second online session. And it has been a pleasure. And I thank you and looking forward to seeing you next week.
All right. Bye, Professor.
Bye-bye. Thank you.
Thanks, Prof.
Thank you.
Thanks, Prof.
Thank you.
Thanks, Prof.
Thank you.